All right, subscribers, welcome back to another episode of Science with Surback. So today what we're going to be talking about is section 22.4 in Chemistry 1. And what this does is it looks a little bit more in depth and in detail about where those carbons and where those hydrogens are placed in hydrocarbons. So 4 objectives I want you to be able to meet by the end of this video. Objective number 1, distinguish between the 2 main categories of isomers, which are structural isomers and stereoisomers, and then differentiate between cis and trans geometric isomers. Objective number 3, recognize different structural isomers given a structural formula. And then the 4th objective that you should meet by the end of this video is describe the structural variation in molecules that result in optical isomers. So we start out here with what is an isomer. And so an isomer is just defined as 2 or more compounds that have the same molecular formula but different molecular structures. So this is a pretty broad definition, and even me initially when I see this definition written down, I still don't fully comprehend it. So it's really good to have some examples to go along with it. So these 3 examples that are down below, all of these things are isomers of one another. And so if we look back on the definition here, they are going to have the same molecular formula. So for pentane, all of these have a formula of C5H12. So if we were to draw the structure of pentane, what we would do is we would have CH3. We would connect that to another carbon. We would have CH2. Connect it to another carbon, CH2. Once more, CH2. And then we would end that with that CH3. Now you can count that up, but there are 5 carbons and there are 12 of those hydrogens. Now, 2-methylbutane is an isomer of pentane. And so again, the molecular formula is just going to have the formula of C5H12. But this time we're going to have to draw our structure a little bit differently. So the first thing that I'm going to draw here, because I have butane, I'm going to draw 4 carbons connected together. So 1, 2, 3, and 4. And then it says at carbon number 2, I have a methyl group. Now, because I have a little bit more room on the right-hand side, I'm going to call this carbon number 2, where my pencil is, and I am going to attach a methyl group, a CH3 group. Now, I'm going to add in my hydrogens. Remember, each thing needs a total of 3 connections, so this would be what we obtain for that. Now, just to double check to make sure it does have that formula of C5H12, I count my carbons, which is 1, 2, 3, 4, and 5. And then my hydrogens, I have 3 plus 2, which is 5, plus 1, which is 6, plus 3, which is 9, plus another 3, which is 12. So it does, in fact, add up to that molecular formula. So both of these 2 things are the same molecular formula, but you can see by just me drawing these simple examples, they are definitely not formed the same. They definitely don't have the same shape. And so now we get down here to 2,2-dimethylpropane. And so again, because it's an isomer of our first structure there, it's going to have the same molecular formula, which is C5H12. Now, we get to this, propane. Propane, remember, is 3 carbons connected together. So I'm going to draw 3 carbons connected together in this fashion. And then right here, it says there is, at carbon 2 and carbon 2, a dimethyl group, which means off of carbon 2, there has to be a methyl group, and then off of carbon 2 again, there has to be a methyl group. Now all we have to do is go back in and add our hydrogens. So to this one right on the right-hand side, we need 3 additional. To this one on the left-hand side, we also need 3 additional hydrogens. Remember, we want a total of 4 connections, so that's where we obtain this value. Now, I like to double check to make sure it does in fact add up to that molecular formula of C5H12. So I count my carbons, 1, 2, 3, 4, and 5 in the center. That's good. And then I add my hydrogens up. 3 plus 3 is 6. 6 plus 3 is 9. 9 plus 3 is 12. So these are all isomers because they have the same molecular formula. They have the same components or the same atoms in that formula, but they are definitely arranged differently. They definitely have a different shape. So now what we need to do is look specifically at each category of isomers. Isomer is just a really broad category for saying, hey, it's going to be the same formula, molecular formula, but it has to be differing in some ways. And so that's why on page 2 here, we start out by talking about structural isomers. So structural isomers, what these are, they are just defined as compounds with atoms that are bonded in different orders. So a great example of those structural isomers are found in those examples we started this section off on page number 1. Those you could see were all having different orders or arrangements of those atoms that were connected together. Now, one thing unique with structural isomers is that they're going to have different chemical and physical properties even though they have the same molecular formula. So a good example of one of these properties is the boiling points of structural isomers with that formula of C5H12. So that is the same example at C5H12, the same molecular formula that we looked at on page number 1. So all 3 of those structures, even though they have the same formula, they're going to have different boiling points and melting points, and they're going to have different chemical reactivity just because of the way they're structured or way their atoms are positioned in that particular molecule. Now, one thing to note here is this. As the number of carbons in a hydrocarbon increases, the number of possible structural isomers also increase. So again, this is kind of a duh common sense thing. Hey, the more carbons and hydrogens that you have in a formula, the more possibilities you have to arrange them. But just to give you an idea, just to give you a couple examples here, in the molecular formula of C7H16, there are 9 structural isomers that can be produced from that particular molecular formula. And again, just to emphasize how expansive this can get, the molecular formula that is C20H42 has 316,319 different structural isomers. So as you can see, the possibilities are almost endless in terms of structural isomers and how many different variations that we can have. So another thing to remember with structural isomers, that those first 3 examples that were shown on page 1 are perfect examples of structural isomers. So now what we can move on Now what we can move on to is another variety of isomers. So we'll flip the page here and we will move on to something known as stereoisomers. So with stereoisomers, again, it's just another variety of those isomers, which again, same molecular formula, but they're formatted a little bit differently. And with stereoisomers, we simply have a definition of stereoisomers as isomers in which all atoms are bonded in the same order but are arranged differently in space. So this definition, probably at first glance, seems like it's a lot broader and it's a lot harder to wrap your mind around it. Well, you just have to do some imagining. You just have to do some mind-opening things to realize what we're talking about. And this case right here, or up and coming, will dictate where those H's and where those carbons are placed. Before I said, hey, you can put it on the top or bottom of that longest chain. Well, now not so much. So there are two types of stereoisomers. We can further divide this to be able to categorize some different classes of organic molecules. The first of which is a geometric isomer. And I'm not going to get into the details because that is the next thing that we go over. But the other type of stereoisomer is an optical isomer. So again, we can just further classify isomers into stereoisomers, and we can subcategorize that into geometric and optical isomers. So what we'll do now is we will transition to talking about the details of each of these types of isomers. So we will start out here with geometric isomers. And geometric isomers are defined as isomers resulting from different arrangements of groups around a double bond. So the key thing here with a geometric isomer is we need that double bond, and it plays a really critical role into how we see and how we actually draw the structure of this particular isomer. Now, what the double bond does in the specifics and details here is it prevents carbons from rotating, and it essentially locks those atoms in place. So with this double bond, think of building a bridge. If you want to make it stronger, you add more supports. Well, as you add a double bond, you're making that connection between those carbon atoms stronger. And you have to remember, there is constant motion in every single atom and every single molecule. So by placing that double bond on that particular organic molecule, what you're doing is you're not allowing as much freedom of rotation, or you're essentially honing in on where those atoms can actually maneuver. Now, what this really does is it's going to affect the isomer's physical properties, such as melting and boiling points. So again, as you add a double bond, you are essentially strengthening that molecule, and as you add strength, the things like melting and boiling points, they will actually increase. Now, within geometric isomers, because we have a double bond, we can actually draw the same organic compound in two different forms. So there are two different forms of our geometric isomers. The first of these forms is known as a cis form. And that is a prefix. That's why you see this hyphen, this dash here. But a cis form is an arrangement in which the two methyl groups, or the two attached groups, doesn't have to be methyl, are on the same side of the molecule. And then our other type of geometric isomer is a trans geometric isomer. And now in a trans geometric isomer, again, that is a prefix, that's why you see that hyphen there. But in a trans geometric isomer, we have an arrangement in which the two attached groups connected to that double bond are on different sides of the molecule. Again, trans means that the molecule, those attached groups are on different sides. Now, it's kind of hard to see this, and I'm out of room on my page here, so I'm just going to grab a blank sheet of paper. And with this here, I just want to demonstrate one example of a geometric isomer. So what we'll do here, I'm going to put this out to the side for a second. What we'll do here is we'll go over an example of a geometric isomer. And our example is 2-butene. And so with 2-butene, there's actually two different ways that we can draw this particular structure. So without getting into the details of cis and trans at this moment, what I'm going to do here is I am going to draw each of these two versions. So the first thing to recognize is butene. That means we have 4 carbons connected together, and I'm going to draw it in a unique way. So I'm going to have a carbon connected to another carbon, and then I'm going to have a little space here, and I'm going to connect our final carbons. And I did this in a really unique way, and here's the reason why. The other thing is I'm going to, no matter which way you number it, this is always going to be carbon number 2. So that's where my double bond is going to occur. And now remember, ENE is that double bond. Now what I'm going to do is this. I am going to connect or add on just the hydrogens for these middle carbons. Now you can see that each of these things already have 1, 2, 3 connections. So that means that these will only have 1 additional hydrogen. Same thing over here. Again, has 3 connections. We just want 1 additional connection. The last thing that I want to do here is I want to add a H's onto these in groups here. So they only have 1 connection. They need 4, so they need 3 more H's to get to that 4th. Same thing up top here. Have 1, want 4. So our molecule looks like this. Now, if you take a look back on those notes, we have this. The attached groups are on opposite sides. See how you can almost divide this molecule in half, and you have one of these attached groups up top and one of them on bottom. They're opposite from each other. And if it's drawn like this, this particular form would be called trans 2-butene. And it's all because these attached groups, in this case CH3, are on opposite sides of that double bond. And that's how we would draw it. Now, on the other side of the story, we could draw this same molecule in this form. So, and this time I'm going to connect my carbons together. And I'm not going to have that last one come down. I'm actually going to have it come up. Now again, no matter which way you spin it, this carbon will always get the double bond because either of those are carbon number 2. And then we can talk about where to put the H's around these carbons with the double bond. Well, again, we put it, just one of them connected to that C. And then over here, it has 3 connections as well. So we have one of them connected to that C. Adding the H's over here, we have CH3, and same thing here. Now, it may not look like much, but the attached groups, in this case the methyl, is on top, and each of those H's are on bottom. So in this case, if you look at the cis, it says the arrangements of the attached molecules are on the same side. So this arrangement right here is cis to butene. So that's how you identify if you have cis or trans. You essentially look at the double bond and you say, hey, where are my attachments coming off of? If they're on the same side, like we have here, it's cis. If those attachments are on different sides or opposite sides, it is a trans geometric isomer. So now that we have that, we have geometric isomers, we got a good example, we can move on to optical isomers. And so with optical isomers, we have to think a little bit differently. And it's a little different mindset of thinking with our optical isomers. So with optical isomers, we start out with the definition here. They're just defined as isomers that result from different arrangements of 4 different groups about the same carbon. So this is a little bit more difficult to see, so I'm going to give you a generic example here, and that is this. So let's say we have our carbon here, and we have 4 different attachments. Now, I'm not going to use any element, and I'm not going to use any particular example, but we'll just call this W, X, Y, and Z. And each of these letters that surround the carbon are different. Now, they could be a chain of carbons. For example, here you could have a propyl group branching off this one carbon here in the center, and over here you could have an ethyl group, or you could have something like a chlorine or hydrogen. But the key thing is that if you look at this carbon that they're identifying in this optical isomer, it has to have 4 different things or number of things that branch off of it. So again, you could have 2 carbons on this side and only 1 carbon on this side, and it still count as an optical isomer. Now, the reason that these things occur is because of the asymmetric carbons. So again, what we mean by asymmetric carbons is that none of these things are exactly alike. They may be carbon chains, but one may have 2 carbons versus a 3 carbon, and that's slight enough to make a difference. But in particular here, asymmetric carbons are carbon atoms that have 4 different atoms or groups of atoms attached to it. Another key thing with our optical isomers or our asymmetric carbon is that you cannot rotate the 2 arrangements in any way that will make them identical to each other. So I should have added here, but this will help make an example of this. We could just as easily rearrange these different attachments, and we could have them like this. And no matter what we do, we could flip, we could rotate, we could do whatever we want to this left-hand side one, and it's never going to result in this particular arrangement. So that's what that bottom point is talking about. Hey, because there's 4 different attachments, it's really hard to flip, rotate, and exactly match this left one to this right one. So our final thing to talk here about optical isomers is that these things, because these carbons have 4 different attachments, what happens here is they result in chiral molecules. And so chiral molecules are a unique form of an optical isomer. What chiral molecules are they are molecules that are mirror images of each other. And so the best way to explain a chiral molecule is your hands. So if you take your hands and you put them together, they form a mirror image with each other. Now, the reason they're classified as an optical isomer is if we try to put one hand on top of the other and try to exactly match up everything, we will never be able to do. I can rearrange my top hand, my right hand, and I can try to rotate, flip, do whatever I want. It is not going to look exactly like my left hand. And so because of that, we call these mirror images of each other. And if a molecule, if an organic molecule acts in this way, we're said that they have, or we're telling you that they have mirror images, and that mirror images is what we know as a chiral molecule. Now, they do have two types of forms. They have a D form, which is the right arrangement of a molecule, and they also have an L form, which is a left arrangement of the molecule. And so again, we go back to the hand example here. Again, the hands, you put them together, they form a mirror image. My left hand would be considered the L form, and then my right hand would be considered the D form of a chiral molecule. And they're a chiral molecule because A, they're mirror images, and then B, they cannot, if you try to put them one on top of the other, they cannot directly match with each other. And that's why they're considered an optical isomer. Now, with chiral molecules, what it causes is it causes optical isomers to have the same physical and chemical properties, except the difference is what happens in chemical reactions. Now, the chiral molecules, they can get a little bit more detail in the weeds of things, but just FYI, so these different forms actually play a role into prescriptions and play a role into drugs. One of the famous drugs, thalidomide, actually had a chiral molecule. Specifically, we call that an enantiomer, and one of the form would help with anti-nauseation that pregnant women would have, and the other would cause birth defects. Now, there's a lot more chemistry involved in that. Fortunately for the United States, it was not allowed. The FDA never passed it, but in some European countries they used it, and it's an interesting read if you just search thalidomide on the internet. So the last thing is this. We have to get to this subject known as optical rotation. And so with optical rotation, we essentially carry over exactly what we talk about here with our business on optical isomers. So what optical rotation is it's going to occur when polarized light passes through a solution containing an optical isomer and the plane of polarization is rotated. And depending on what type of molecule is in there, it's going to rotate to the right by a D isomer. And then if it's an L form of that isomer, it's going to rotate to the left or counterclockwise if you're looking at the light towards that light source. So those different types of isomers, or those different forms that we talked about with a chiral molecule, will really determine how this light is rotated. And the reason that we're talking about this is how we identify it in a particular mixture. So when they run an experiment, scientists run an experiment, they can place it in a particular device that uses this polarized light, and we can determine what type of form that organic molecule is. Now, polarized light has to be used for this process because it is light that is filtered or reflected in such a way that results in waves all to lie on the same plane. And then the last point that I want to make here is that optical isomers are given their name because they affect light passing through them. So to give you a little idea here, I don't have the best image, but this is how this would work. So this device here, if we zoom in a little bit, you essentially have a sample of that liquid organic compound, and you shine light. It goes through this polarized plate here, similar to like polarized sunglasses, and it filters that light. And then you can see here that the light, once it passes through one of these two solutions, is going to bend one or two ways. If it bends like up here on the top form here, that's the counterclockwise rotation, you get an L form, and down here you get clockwise rotation of that light, and that is known as that D form. And that's of this particular molecule here in this example. Again, not the best setup here, but it does give you a little background, give you a little bit of emphasis of what we just talked about. So we went through a lot. We added a lot more detail with this section. The big takeaway of this section should be it matters now where I put my carbons and where I surround those hydrogens with. So I hope you've enjoyed another section of Science with Surback. This concludes section 22.4. And as always, remember to subscribe.